So now we will discuss Euler products. The reference is an additional text which is posted on the class website. To start with, let me recall a Riemann's zeta function. We discussed this function a little bit in the connection of two Bernoulli numbers. So the values of Riemann zeta function, it is defined, by the way, as zeta of s to be the sum from n equals 1 to infinity and to the negative s. The series converges for s big enough, defines a function. So s is the variable for the function. So this function maybe is interesting from many perspectives, and as you probably know, is one of the central objects in mathematics. We take everything lightly. Here, we will not consider deep properties of this function, but we have already learned that values of this function are at certain points for certain values of s are Bernoulli numbers. Today, I want to discuss this function from a different perspective. I want to say, first of all, that this is also a generating function which we consider generating functions a lot already in the class. We discussed certain generating functions. Let me recall. Generated for a sequence, so let a n be a sequence. For a sequence an, we constructed generating function f of x to be sum from 0 to infinity a n x to the n, and this was generating function. The idea was that this function somehow incorporates the information about the sequence. So we have sequence, we have infinitely many numbers, and we incorporate all of them into a function. X is the variable, and this function, somehow the properties of this function can tell us something about properties of all objects taken together, all numbers from the sequence taken together. One may also construct a generating function from a sequence in a different way. So also a generating function, a sort of generating function, is presented by the following series: L of s to be sum. Now I want to start with 1, not with 0. An n to the minus s. Now, this is also a series now convergent for some values of s. If the weather is good enough, for s large enough, the series may converge. So I started summation with 1 because I don't want to write 0 to the negative power. And this is also called sometimes, quite frequently, L function. Or directly L series. The idea is very similar. Again, out of a sequence, out of many objects, we want to construct one function, L in this case. S is the variable, and this function L of s somehow incorporates properties of all objects taken together. Of course, function L does it in a completely different way than the function f does it. It may be interesting and produce some interesting information about the sequence an to construct this or that function, maybe both. Very much depends on the sequence of numbers a sub n under investigation. Now, Riemann zeta function is a member of this family of L functions, a pretty prominent one, and I want to attract your attention if A is a sequence which consists of all ones. An is 1, whatever n is. In this case, this function f is very simple, that becomes geometric series. So a special case, let me write it. So examples. Here is a n equals 1. In this case, f of x is sum from 0 to infinity. Well, let us say that the sequence begins with 1. Oh, doesn't matter. Maybe with 0. So f is sum from 0 to infinity. A of n is 1. So we have just x to the power n. And this is, of course, the sum of geometric series 1 plus x squared plus so further. And we have that it is equal to 1 over 1 minus x geometric series. With the same sequence, all an's are equal to 1, we have the function L of s as sum from 1 to infinity If n is 1, we'll skip it and write n to the power minus s, which is Riemann zeta function. So you see, with this sequence, this function, this generating function is very simple, does not really produce much information about the sequence. The sequence is not very interesting, so that was not a surprise. However, even for this very simple sequence, the generating function turns out to be, L function turns out to be highly non-trivial. That is also interesting. So this Dirichlet function is probably much more difficult, but maybe much more interesting if, even for a very simple sequence, it gives us a non-trivial outcome. So this type of generating function, Dirichlet L function, this type of generating functions is especially interesting when the sequence comes from an arithmetic function. We study arithmetic functions, so we may look at sequences coming from arithmetic functions. Namely, for an arithmetic function, f, I recall, what does it mean arithmetic? That means the domain of the function is a set of positive integers. Now we set a sub n to be f of n. So in this way, an arithmetic function f generates a sequence of numbers, the values of arithmetic function for n bigger or equal than 1. Therefore, that checks with the definition of Dirichlet L series of our L functions. We start the summation with 1 always, not with 0 as we frequently did with those generating functions. So from this perspective, Riemann zeta function comes from f equals I. You remember we had the function I, a very simple function, which takes a value of 1 no matter what. So I of n is equal to 1. We will rewrite what we have as L f of s in general is sum from n equals 1 to infinity f of n to the power minus s, in particular with this notation Li for the function I is going to be f of n is now I. F equals I. So Li of s is sum from 1 to infinity I, which is always 1, n to the minus s, zeta of s. So zeta is, Riemann's zeta is indeed a member of this family of Dirichlet L series of generating functions of this kind when the sequence an comes from arithmetic function which is I. So these Dirichlet L series in general are considered for quite a bunch of sequences, typically indeed coming from certain arithmetic functions. And these L functions are especially interesting when the arithmetic function is multiplicative. Remember, last time, all arithmetic functions which we consider are multiplicative. So let us see what happens with an arithmetic function f, or with the Dirichlet L series, with our L function, f the arithmetic, it comes from a multiplicative arithmetic function. So from let, and in this case, what we obtain is Euler product. This is kind of proposition. Euler product. Or let f be a multiplicative arithmetic function. Then the generating function Lf of s, defined in this way, has an Euler product. L f of s is equal to sum is defined as the sum f of n to the negative s, n is equal to the product over primes p of sum from m equals 0 to infinity f of p to the power m, p to the power negative ms. It looks like the expression in the right, which is called, this expression is called product over primes, is called Euler product. It looks like this Euler product is less interesting and convenient than the definition we use. Indeed, here we have only one infinite operation. This is infinite summation over n, while here we have two infinite operations. We have infinite summation over m from 0 to infinity, and we have a product over all primes. So I will remark here that this is notation. This is even not a remark, but notation. This symbol means the product over all primes p. If there is another letter here, q, then the product runs over all primes, which are denoted by q. In parentheses, there is an expression which depends on your prime. So every term depends on the prime. And we take a product over all primes. I will not really prove this proposition. I rather explain that the proposition is obvious, does not really require serious proof. I will let me explain how it comes. This is what is called a formal manipulation with power series. So some clarification. I will try to convince you that this identity, this proposition, does not require proof. It is obvious. Let me try to do that with a clarification instead of a proof. We let P and Q be two different primes. And consider not infinite product, but the product of such expressions over with just two primes instead of infinitely many, as this symbol requires. Sum over m from 0 to infinity f of p to the m p to the minus ms times sum. I will write another variable of summation here, because otherwise, if I write m here and m there, we may get confused. And from 0 to infinity, f of p to the n, p to the negative ns. Now I will proceed with the manipulation with series, with sums, which we have seen last time. The difference is, last time we did it with finite sums, and now we'll do it with infinite sums. So we multiply every term from here by every term from here and add everything together. In this way, we get a double sum over m and n from 0 to infinity, f of p to the m, f of p to the n, p to the minus ms, p to the minus ns. What we see is a sum over all pairs m and n run over all pairs of integers f of p to the m times f of, oh sorry, what am I doing? This should be q, otherwise it's not good at all. Q, and this should be q, and this should be q, and this should be q. Let me correct everything. So we took two different primes, and this is a series with p, while this is a series with q. Now, f of p to the m times f of q to the n. We assumed that f is multiplicative. P and q are different primes. Thus, p to the m and q to the n are relatively prime. So that is what does it mean to be multiplicative. I can write it as f of p to the m, q to the n. Here, it is pq, no, it is p to the m, q to the n, minus m minus n to the power s. P to the m, q to the n, I will write it this way, to the power negative s. And now the series we obtained here is quite similar to the series which stands in the definition of our L function. We can write it as sum over, say, k in some set S. In a moment, we'll see what the set S is. So we sum over all k, f of k to the minus s. The set capital S is all k's Let me write it in words. That's easier. S are positive integers of the form p to the m, q to the n, where with m and n bigger or equal than 0. So here the summation takes place over all positive integers, which decompose into this kind of product of prime, a product of powers of our two primes p and q. Now it should become clear that if we took three such terms and multiply them together, not two, as we did here, but three for three different primes, same kind of manipulation will lead us to the sum over all integers, which can be presented as a product of powers of three different primes. And finally, when we take the product as here over all primes, we get this kind of series, same kind of series, with a summation over all positive integers, which can be presented as products of powers of all primes. But we know the fundamental theorem of arithmetic, which tells us that this is the set of all positive integers from 1 to infinity. So when we take product over all primes, we get the summation over all positive integers, as we wanted here. So the product over all, not just two primes, is the summation over all positive integers. That is an explanation why, for a multiplicative arithmetic function, Euler product identity takes place. All right. So, an example of as an example of Euler product, let us consider our very first example, Riemann's zeta function. Riemann's zeta function is sum 1 to infinity n to the minus s. And according to this product decomposition, should be a product of sums m runs from 0 to infinity. What kind of sum do we have here? Our function, what is our function? Our function here is function I, which is 1 anyways. So this is 1 p to the power m minus ms. P to the power minus ms. What do we have in parentheses? This is a geometric series. This infinite sum is a sum of geometric series. So we get product over all primes. And let us sum the geometric series. It starts with 1, p to the minus m, p to the minus s, p to the minus s, p to the minus 2s, p to the minus 3s. Altogether we get 1 minus p to the minus s. Or sometimes we write it as product over all primes 1 minus p to the minus s, taken to the power negative 1. This identity, the factorization of zeta function as a product over all primes, of course, goes back to Euler, and it seems to be quite trivial. Let me give you the first consequence of this identity. We will discuss first of all this one. You probably know a theorem which goes back to Euclid. The set of primes as infinite. Euclid proved the theorem. We probably already mentioned that in this class. We had a chance to discuss that. Euclid's proof is very well known. I will only briefly repeat it. So what Euclid's proof is about? Assume there are only finitely many primes. So we have a finite list of primes, we multiply all of them and get a number. We add 1 to this number. What we have it produced in this way is not divisible by any of our primes, simply because it gives a residue of 1 being divided by any of our primes by construction. If it is not divisible by any of our primes, this should be a prime, and this prime is of course bigger than all primes in our list. So we assumed that we have a finite list and constructed a prime which is not on the list. This is a contradiction which implies that the set of prime numbers is infinite. Probably that is one of the first theorems proved in mathematics. The theorem has more than one proof, and now I want to show you Euler's proof. Invented, 1700 years after Euclid. And this proof uses completely different ideas. So this proof is based on this example which we have just written. We have the identity, sum from 1 to infinity n to the minus s is equal to the product over all primes 1 minus p to the negative s. What is that? This is an identity of two functions in S. S is the variable functions in S, meaning that two functions are equal. This is the same function. So left-hand side and right-hand side is the same function in S. Now let us look at the domain of this function. So identity of two functions in S means, in other words, this is the same function. Now let us consider the following question. Is S equals 1 in the domain of this function? Well, if we look at this representation of our function, then the answer is no. Because the harmonic series sum from 1 to infinity n to the negative 1. When s is 1, this is n to the negative s becomes n to the negative 1, which is 1 over n. Diverges. We know this fact from calculus. Harmonic series, this sum 1 plus a half plus a third plus a fourth plus so further diverges. So S equals 1 is not in the domain. At the same time, if the amount of primes, this is product over all primes, if the amount of primes is finite, then the answer is going to be yes. Yes, if there are only finitely many primes, because this is as we get a finite product on when s is -1. This is going to be a product I multiply by p minus 1. This is a number if the amount of primes is finite. This contradiction shows us that the assumption that there are only finitely many primes is wrong. The contradiction implies that this set of primes is infinite. Done. So we proved Euclid's theorem with an essentially different argument. This was Euler's argument. That becomes already interesting. So the presence of Euler product allows us to find a different proof of a very fundamental fact in mathematics. That means that the Euler product is valuable. Of course, it doesn't allow us, it allowed Euler to do that. I have probably to address some subtleties in this proof. You may well ask me, why did I use S to be 1? See, if you take not 1, but something negative, say, then the series on the left converges even stronger. So, some remark. Y s equals 1. In this proof, what we want to do. We want this series to diverge. It diverges for negative s, say the series diverges even better than it diverges for s equals 1. S equals 1, if you remember from calculus, this is on the boundary. You have to work a little bit to show that this series diverges, while there are no problems with the product unless s equals 0. Finite product will also always be a finite product of finitely many quantities that well exists. So, for example, it looks like a good idea to put s to be -1. Say, why not s equals -1 with sum on the left. This sum becomes S is negative 1, sum n. Negative 1 is 1, n to the 1 is n, which is 1 plus 2 plus 3 plus... Of course, the sum also diverges, and you do not need to, because the terms grow unbounded. You do not need the subtle estimate with logarithm, with integral, whatever, to find that this series diverges. Point is, I never told you what kind of variable S was. And you tacitly assumed this is a real variable, while I assumed this was a complex variable. Still, what's the difference? This is 1, a real number. However, you may find elsewhere Ramanujan's identity. One plus 2 plus 3 plus 4 plus 5 plus equals negative 1/12. I will not go into explanations what does that may mean at all, and why this identity is actually true. You have to make sense out of that, and that requires us something different from elementary number theory, which to understand this kind of identities, you need the concept of analytic continuation, that is advanced complex analysis, not elementary number theory, which we study in this class. Nevertheless, difficulties arise. Maybe this negative 1/12 is a finite product with finitely many primes, and there are only finitely many of them. So of course there are infinitely many primes, but there is a subtlety here. Saying taking S equals 1, we pay a price. Here we took S to be 1. We pay a price. We get not the most pleasant series to analyze, but we avoid this strange discussion with crazy Ramanujan identity. What can that mean whatsoever, if at all? So, to sum this discussion up, Euler's proof is absolutely correct with S equals 1. It may go through with other values of S, but really better to take S equals 1 here, to avoid deep and difficult justification of steps. We will not go into that deeper. I just want to say that this actually, although this remark seems to be a counter-argument, it is not. Well, it is not on primitive level because to make a counter argument to Euler's proof out of Riemannian identity, you got to explain what does Riemannian identity mean. What may it mean? After that explanation, you better save Euler's argument with s equals 1 than with s equals -1. Oh, this was -1. The sum shows up when s is -1. So this is just a remark about a subtlety in the argument. Anyway, the proof is absolutely ingenious. In some sense, Euler's proof is way better than Euclid's proof because you may develop it further. It tells you something about the relation zeta function and primes. Because next question would be, there are infinitely many primes, but how dense they are among other primes, among other integers. When I try to answer this question, Riemann's zeta function shows up naturally. The first appearance of Riemann's zeta function in the connection with this question is here in Euler's proof of infinitude of prime numbers. Now, all that is about Riemann's zeta only. So, at the same time, the Euler product here is good for any multiplicative arithmetic function. We could have a supply of multiplicative arithmetic functions. A natural question would be whether we can produce something interesting when we take for f here another multiplicative function, not necessarily I, when we produced Riemann's zeta function. What happens when we consider L functions as a generating function for the values of some arithmetic function besides function I? And the answer is nothing, not much. Not exactly nothing, but not much. So the question we want to address, what happens when we take other functions? Here is the answer. Theorem. This is theorem 1 in additional text. Take mu so L mu of S is defined as sum from 1 to infinity mu of n to the negative s. This is the definition. The theorem claims that what we produce is 1 over zeta of s. Take sigma, L sigma of s, by definition is going to be sum from 1 to infinity sigma of n n to the negative s, and the theorem claims this is nothing but zeta of s times zeta of s minus 1. Take d, L d of s is sum from 1 to infinity d of n to the negative s. The theorem claims what it produces is zeta of s squared. Finally, L phi of s. So we have the definition of LF for an arithmetic function f. We take various f and see that every time what we produce, this LF, well, the definition is here. This is LF, our first definition for various arithmetic functions, is not far away from the simplest function every time. We get something closely related to Riemann's zeta function. Sum from 1 to infinity phi of n to the negative s. What we get this time is zeta of s minus 1 divided by zeta of s. That suggests that we get something related to Riemann's zeta every time, which is absolutely wrong. That is just a feature of our consideration. We considered only very simple arithmetic functions. With that, we indeed do not leave the realm of Riemann's zeta function. There do exist an abundance of arithmetic functions when what you produce is not Riemann's zeta, but something completely different. L functions is a really rich family of functions, although they have very deep common properties. Just what we considered in this class would yield variations on the theme of Riemann's zeta. There is an exception, but the exception is trivial L delta. Remember, delta function, it takes the value of 1 for n equals 1 and is 0 otherwise. Sum from delta of n to the negative s, but from 1 to infinity, but delta of n is almost always 0. We end up with only one term which survives, namely with n equals 1. Delta 1 is 1. And n is 1 to the negative s, which is also 1 independently on s. So this is 1. In this case, the function is not related to Riemann's zeta function, but it stays trivial and not very interesting. In the additional text for this theorem, the proof is given for function g. That is probably the most difficult one, as difficult as sigma, among the most difficult. This is proved in the additional text. Let me now show you something simpler so you get warmed up and get ready, if you want to do that, to read the proof and the additional text about this identity. Let me start with an easy thing, mu. So 1/3 or before even I start any proofs, I want to say that all these proofs, all these facts are proved using Euler product. So we desperately need this proposition from the very beginning. We desperately need this proposition. Let me copy this proposition beforehand. So I will use sum from 0 to infinity f of n to the minus s is equal to the product over all primes, the Euler product decomposition, sum m runs from 0 to infinity, f of p to the ms, p to the ms. We will use that. So this proof, which something I will show you now, something you may, this one you may read in the additional text anyway, that demonstrates how useful this decomposition is. So we start with function mu. So 1/3 this one. So I will rewrite it here. Sum from 1 to infinity, mu of n to the minus s, oops, sorry, equals this one, 1 over zeta of s. I will write it because I will not prove all of them, so I want to prove this one now. So by the multiplicativity of mu, this is for multiplicative functions f. So mu is a multiplicative function. So therefore, we have that sum sorry, it was a typo. Sum mu of n to the minus s according to this Euler product decomposition for multiplicative functions. Mu is multiplicative. We can write that this is product over all primes, sum from 0 to infinity, mu of p to the ms divided by p to the power ms. Oh, what do we remember about the function mu? Oh, sorry. Too many typos. Sorry, this is a typo. P to the m elsewhere. So it is p to the m, and this is p to the m, not ms, of course, because f of p to the ms does not define the domain of our arithmetic function f. All positive integers s may be complex, may be real, not necessarily integers, so will not make much sense with ms here. Mu at p of p to the m, what is that? We can calculate it. Mu of p to the m, this is, if m is 0, this is mu of 1, which is 1. 1 if m is 0. If m is 1, this is mu of p, p is a prime, that composes into a product of 1 prime, negative 1 to the 1 is negative 1. Negative 1 is m is 1. And that's the end of story. When m is bigger than 1, this number, p to the m, is not square free. It's divisible by m squared. So mu is 0 in all other cases if m is bigger than 1. All right, so thus this is the product equals to product. What is left out of the whole sum? 2 terms. Whatever the prime p is, only 2 terms are left, with m equals 0 and with m equals 1. When m is 0, mu is 1, and this term is 1. Everything is 1. When m is 1, mu is negative 1. M is 1. Okay, this is product over all primes 1 minus p to the negative s. And this is equal to 1 over zeta of s, because zeta of s is, we have recorded it somewhere, zeta as, here it is, zeta is the product 1 minus p to the s to the negative 1. Product over all primes 1 minus p to the negative s to the negative. So this zeta is the product of all these same factors, every one taken to the power negative 1. Thus, we got the identity. So, you see, here is another identity, the last one for today, a little bit more involved. Wanted some phi of n to the negative s, and runs from 1 to infinity, is equal to zeta of s minus 1 divided by zeta of s. We again use Euler's product, this Euler product decomposition. We can do that because the function phi, Euler's function phi, is multiplicative. Thus, we can write that the sum phi of n to the negative s is equal to the product over all primes sum m runs from 0 to infinity phi of p to the m divided by p to the ms. Similarly to the previous case, the key is the calculation of this sum. Why we succeeded to prove this identity? Because we succeeded to simplify this infinite sum to a very simple finite sum. Let us try to evaluate somehow this infinite sum. For that, we will use an explicit formula for phi, for these values of function phi. This is example 6-1 in the book, where phi is calculated. In fact, we did this calculation in class. This is either 1 if m is 0. Phi of 1 is 1. If m is bigger than 1, that is what was calculated in this example. This is simply a part of the definition. What was calculated in this example, 6-1, that this is p to the m minus p to the m minus 1. F m is 1 and bigger. Thus, let us try to calculate the sum from 0 to infinity phi of p to the m divided by p to the power ms is equal to, we have to single out the term with 1. This is not regular. For m equals 0, this expression will not give us the correct answer. This will give us 1 minus 1 over p, which we don't want. So we single 1 out. When m is 0, this is 1, and this is 1, and this is this 1 over 1. What we left was what is the sum from 1 to infinity. Now we have p to the m minus p to the m minus 1 divided by p to the ms, which is the same thing as 1 plus sum from 1 to infinity. I divide the difference by denominator, 1 minus s to the power m, p to the power 1 minus s times m, minus this minus here, sum from 1 to infinity p to the power 1 minus s times m minus 1 minus s. Which is equal to, now I take this one inside the sum. This is going to be a sum from 0 to infinity. If m is 0, which is not allowed here, this is 1. So let us write sum from m equals 0 to infinity p 1 minus s m minus, and here I take this p to the power minus s out, and inside I shift the index of summation by 1, making this m instead of m minus 1 and this 0 instead of 1. The sum becomes 0 to infinity p 1 minus s m which is, the two sums are the same, 1 minus p to the minus s times sum from 0 to infinity p 1 minus s m. This sum here is again as in the previous case, in the case of, which was the previous case? No, there was no previous case here. Sorry, the sum here, not as in the previous case, but this is the sum of geometric series. P to the 1 minus s to the 1, 0, 1, m runs 0, 1, 2, 3, and so further. We sum them together. The number p to the power 1 minus s raised to many different powers let us sum this geometric series. So we have 1 minus b to the minus s, and the sum of geometric series becomes 1 minus 1 over 1 minus p 1 to the minus s. What we got is 1 p to the minus s, 1 minus p to the 1 minus s, negative 1. Now, it becomes clear that the product over all primes of these sums, which we just calculated, is equal to product over all primes. We calculated that. 1 minus p to the minus s, 1 minus p to the power 1 minus s to the power negative 1. And that is our answer, because both zeta of s and zeta of s minus 1 have same factors. So the product of these inverse factors is exactly zeta of s minus 1. The product of these factors is exactly 1 over zeta of s. So we get zeta of s minus 1 divided by zeta of s, as we wanted. I'm sorry I did not write it correctly here. I've just noticed. So, no, I wrote everything correctly. I'm sorry. I worried that I did something wrongly. I did not. So, I believe we proved out of these 4 identities, we proved 2, we proved this one, and we proved this one is proved in the additional text. I think that is enough. The proofs are kind of similar. I will not do the last one. And that was all about Euler products. So we started with Riemann's zeta function, defined in this way. We already met Riemann's zeta function in this class. This is our second approach. We looked at that and tried to generalize from here, defining what is known as Dirichlet-L functions. Zeta function, Riemann's zeta, is a member of this family. Dirichlet-L functions may be defined for sequences, but it is more interesting to think about sequences as sequences of values of arithmetic functions. So this is the L function for an arithmetic function f, for arbitrary arithmetic function. For the function I, which always takes the value of 1, this is still Riemann's zeta function. We considered so far, and we bound ourselves with multiplicative functions. For multiplicative arithmetic functions, the corresponding L function decomposes into an infinite product over all primes. This is Euler product. So that thing, although is very simple to understand where it comes from, here is a clarification. The thing is a powerful and interesting tool. For example, the Euler product decomposition for Riemann's zeta function allowed us to come up with a completely different proof based on different ideas, based on ideas of calculus, on ideas of divergence and convergence, completely different proof of Euclid's theorem, a famous theorem, the theorem most people start learning mathematics proofs with. There are infinitely many prime numbers. So Euler came up with a completely different proof. We discussed that proof with a little bit of remark on further justification and a very interesting Ramanujan's identity, which I will not tell you how to interpret. And after that, being that much warmed up, we wanted to find out whether for other arithmetic functions, besides the very simple function which is always 1, the function I, the function which we denoted by I, maybe for other functions there are also interesting Dirichlet L functions. Interesting or not, here that is a matter of personal taste, but all of those which we have considered, look familiar. They are tightly related back to Riemann's zeta function. There are arithmetic functions which are multiplicative and which have Dirichlet functions quite different than some combinations of related to Riemann zeta. I'm speaking about these things as Dirichlet functions for a good reason. Dirichlet was the first, probably, to generalize it so that they began to play a prominent role outside of Riemann's zeta function only. He considered these things which are still very interesting and already do not come from Riemann's zeta function. In this way, Dirichlet generalized the work of Euler. So we gave a couple of proofs of these identities. We tried to convince ourselves that indeed these functions are related to Riemann, these L functions associated to simple arithmetic functions are related to Riemann's zeta function. That's all for today. That was all about the additional text which is posted on our website. Thank you for listening.